unfortunately, I dragged my computer back out and start recording these things again. Got some people counts this thing, so hopefully I'll remember to recording. We need it. Great. So just to remind you, this is where we finished last time. So we talked about path length difference. So again, path length difference is saying that we predict what type of interference we can have, whether that is constructive or destructive interference, based off of the difference in the paths. So again, if I have two sources, like source 1 and source 2 here, each one of these guys, the sound has to travel a different distance to get to a particular point of interest. And then if the path length difference is when my sources are in phase with each other, if they are an integer multiple of the wavelength, then it's going to be constructive interference. And then if they're a half an integer multiple of the wavelength, then it's going to be destructive interference. But if they're originally out of phase, we just switch those. So the problem we looked at was we had two speakers along the y-axis. This one was at the origin, this one was 2 meters above. And then we were looking for anywhere along the positive x-axis where we had constructive and destructive interference. So we wrote down our path length difference and we derived this beautiful expression last time. So now all we have to do is actually solve this expression. So again, for part A, we want to look for destructive interference, which means that n has to be in a half integer multiple of the wavelength. And remember here, we know the velocity, we know the frequency. So in that case, we know that the wavelength is simply equal to the velocity in air divided by the frequency. So we know that. And then for part B, we want to look for all the locations for constructive interference, which means that we're going to choose z to be simply integer. Now again, since I have a negative sign here, as n gets bigger, eventually what will happen is this thing is going to become negative because this term here will be dominant over this term because this is simply a constant. When that happens, we're going to cease and desist calculating because, again, we only care about the positive x direction, not the negative x direction as well. So good. So basically, to do this part A, all we're going to do is we're going to say, okay, let's start off with the smallest n possible value we can have, which is 1/2. Plug in 1/2, and then multiply everything out and find out what this comes out to be. Do it for 3 halves, 5 halves, 7 halves, 9 halves, 11 halves, 13 halves, 15 halves, and et cetera, et cetera, et cetera, until eventually we run out of positive values and get the negative values. For constructive interference, we're going to start off with the smallest possible value of n, which is 0. Okay, for 0, and then 1, and 2, and 3, and 4, and 5, and 6, and then until eventually we get to what we want. So I went ahead and wrote all those things down. So these are the results. So for the destructive interference, start off with n is equal to 1/2. We get the half location then is going to be at 9.01 meters. For n is equal to 3 halves, we find it's 2.71 meters. For n is equal to 5 halves, it's 1.27 meters. N is equal to 7 halves, it's 0.53 meters. And then for 9 halves, it's 0.026 meters. And then after that, we get into negative numbers, so we just stop it. So 9 halves is the smallest possible positive value. For part B, constructive interference, then we start off with the integers. Here I put in n is equal to 0, I get infinity. And the reason for that is if I get 0 here, this term goes to 0. Then I have 4 divided by 0, but anything divided by 0, your calculator will tell you it's undefined, mathematician will tell you it's undefined, a physicist tells you that's infinity. So it's infinity. Derek, is that a question?
Where did you get the y value at?
Y was given in the problem, it was given as 2 meters. So here y was equal to 2 meters. So I was given in the problem. Okay. So let's keep plugging in numbers. From there, we have n is equal to 1 happens at 4.34 meters. N is equal to 2 happens at 1.84 meters. N is equal to 3 happens at 0.86 meters. N is equal to 4 happens at 0.26 meters. And then n is equal to 5 would give me a negative value. So we stop at n is equal to 4. So one thing I want to point out here is notice kind of what's happening at the pattern. So first of all, we'll talk about why infinity here actually makes sense. But this thing says that if we have our speakers here, so this is the location of my speakers, the first place I run all the way into my first constructive interference is way out here at spatial infinity. Then as I start moving in, the next thing I come to is 9.01 meters, which we're going to say about here, which is then destructive interference. So I've gone from constructive interference to destructive interference. Then I keep moving. Next thing I run into is constructive interference again at 4.34 meters. Then I keep going, and then I come into destructive interference again at 2.71, and then I keep going, and then I run into constructive interference again at 1.82, and etc. So what's happening here is that as I'm following along the x-axis here, I'm switching back and forth from constructive interference, so this is my first constructive interference, so this is my x0, to then out here, which is my first destructive interference, so x is equal to half. Then again, I find a constructive interference, which is x1, and then etc. So as I'm moving in, these locations then are alternating. So I go from constructive interference to destructive interference to constructive interference, and etc. So anywhere along here, again, these guys are alternating back and forth. So that makes sense. The next thing to kind of look at is why does spatial infinity actually make sense? So why is it that I have to go infinite distance away from these guys to get my first constructive interference at n is equal to 0? So to answer that question, we first have to think about what does n is equal to 0 mean? What it means is that there's no difference between the two paths. They have exactly the same length. That's what this thing means. Because again, remember, we're saying that our path length difference, which is right over here, delta t must be equal to n times lambda. Okay? Which means that for n is equal to 0, there's no difference between the two path lengths. But here, since this one is automatically up some distance here, the only way to get these two to be exactly the same length is if they're both infinite in length. Which means that these two lines have to be parallel to each other, which means by the time I get out spatial distance infinity away, that little difference of 2 meters basically is nothing when I'm infinite distance away. Which means my two lines are parallel, which means they're exactly the same length, which means there's no difference between the two paths. So this is why infinity actually makes sense for my n is equal to 0. Because they have to be exactly the same length. In that case, that's the only way I can have delta t is equal to 0. But again, the main thing to point out here is that it makes sense that this one has to be at infinity. It also makes sense that these guys have to be alternating back and forth, because as I'm moving through, I'm finding those locations where I have both maximum and minimum amount of interference, or both maximally constructive and maximally destructive interference. Now again, remember, path length difference only tells me the location of maximum constructive interference and maximum destructive interference. It doesn't tell me anything about where those locations are in between those. Okay, so this is path length difference. So this is one type of interference we can have from sound waves. Another type of interference we can have from sound waves are standing waves again. Because if I can make standing waves with any general type of wave, then I have to be able to create standing waves with sound waves as well. So far, we've seen standing waves when I have two fixed endpoints, for example, a vibrating string or Derek playing his guitar. But here, since I've been with sound waves, we have alternate ways we can create standing waves, which are now using another type of instrument, which instead of a string instrument, would now be a wind instrument. So for example, I can have two different types. I can create one which is known as open-open, which means the two endpoints are actually open. For example, this could be a flute. So in a flute, you have a hole on the side here where you blow in through the hole on the side, and then you have little holes in there as well, which then creates different resonance chambers, which means that the length of the tube is changing size, which creates different frequencies. Or I can have what's known as a closed open, where this side is completely closed, and this side is open to the air, which creates a different type of standing wave. And an example of this would be like a saxophone. So anything that has a reed in it. So if you have a reed, it creates then a displacement node, but on the outside, the particles have to be able to move to match that of the air, which then creates a displacement antinode. So basically what's happening here is if I think in terms of displacement, this side has to be a node. This side also has to be a node. I'm sorry, antinode. So this has to be an antinode. This side also has to be an antinode. That's you. This side then has to be a node, while this side has to be an antinode. So good. So let's look at these different types of standing waves that you can create. Now in this case, I'm not going to derive them and go through all that math that we went through last time. We did it once, we're going to have to do it again. This time I'm just going to draw the pretty pictures, just to make it a little easier. So, okay. So first of all, let's look at the first case, which is the open, open. So let's look at the open, open and see what we get. So let's say here is my object I'm going to create. And what I know is, again, in terms of displacement, since this is open to the air, I have to have an antinode. For this one, I also has to be open to the air, which means I also have to be able to create an antinode. So here I have to have an antinode, here I have to have an empty node, which means that the simplest thing I can draw is that. This is the simplest type of thing I can draw. The next simplest type of thing I can draw is this one. So now this has to be an antinode, this also has to be an antinode. So now it's going to go down past 0 to its maximum, past 0 back up to its maximum. So that's the second simplest thing I can draw. The third simplest thing I can draw is this one. So I have to have an antinode here to get an antinode here. That has to be different from the first one, so it's got to go down, up, down, and then empty. And then etc. Okay. Now let's remind ourselves what we drew for the closed, closed, or the fixed, fixed. So in that case, for example, a string, I had to have a node here and a node here. And this thing was the length of my object. So let's draw each one of these. Again, the three simplest ones we can draw. So the first one has to do this. It was a half a wavelength. Next simplest thing I could do was this one, which was a full length length. And then there was this one, which was what? 1.5 wavelengths. Okay. Now what I want you to do is basically compare these pictures on the left, which are for the open open, with these pictures which are here on the right, which are for the closed closed. So how could I change the pictures on the left to get them to look like the pictures on the right? Is that even possible? Yes, it is possible. So how can I change the pictures on the left to get them to be the pictures on the right? So again, here, antinode, but here I have node. Well, what must I do to this picture to make it look like that picture?
Close one end.
What's that?
Close one end.
Close one end. Well, let's think about just the wave itself instead of physically what I'm doing. If I close one end, it's actually completely different. So I'd have to actually close both ends. But let's think about how can I move this wave here to make it look like that wave? Move it to the right by how much?
By half.
By half a wavelength, right? If I took this thing here and I simply moved it to the right by half a wavelength, this wave here would be exactly the same as this wave. What about this one?
Same thing.
Same thing. Move this one by half a wavelength, right? So again, to the right, I now get this wave. What about this one? Same thing. So here, the open open is exactly the same thing as the closed close, just shifted to the left by half a wavelength. Which means that, mathematically wise, all I have done is I've switched that cosine, which was the harmonic oscillator part, and the sine portion, which was fixing the profile. I've switched those two. So now my profile in space looks like a cosine curve, and my oscillator part looks like a sine curve, but I haven't done anything else, which means mathematically they are equivalent to each other. There is no difference between the closed close and that of the open open, at least mathematically. Again, physically wise, what I'm doing is I'm just shifting each one, but it doesn't change the mathematics, which means all those equations that we wrote down before for the closed close are also valid for the open open. They're exactly the same, which means that the wavelength is simply going to be equal to twice the length divided by the harmonic, and then the frequency is going to be the harmonic times the velocity divided by twice the length, where the harmonic is still again equal to 1, 2, 3, 4, and etc. So these expressions that we wrote down before, which were for the closed close, are also true for the open open. These work for both cases. They're indistinguishable mathematically. Everyone's okay? Now let's look at the other case. The other case then is what? The closed open or the open closed. So for this one, I get something that looks like this. We already did this in the lab, but I'm just going to redraw these again anyways, just to kind of remind ourselves. So again, the difference here is I have to have a displacement antinode on this side. I have to have a displacement node on these sides, which means that, again, here I have, let me do it red like I did before, node with an antinode, node with an antinode, and again, node with an antinode. Again, for this one, the simplest way I can draw it is simply this guy, which as we talked about in lab is a quarter of a wavelength. For this one, it has to go up, back through 0 to maximum, so this is 3/4 of a wavelength. And then finally for this one, go up, down, back up to maximum, which means that this is 5/4 of a wavelength. So as we showed in lab, basically what this means then is that the wavelength then is equal to 4 times the length divided by the harmonic, which means that the frequency then is equal to the harmonic times the velocity divided by 4 times the length. But now, since this has to start on an antinode, or start on a node and end on an antinode, I can now only have odd harmonics. So in this case, I only have odd numbers instead of even numbers. So what does that do? Well, that'll basically allow me to create new frequencies which are actually lower than the previous frequencies. Right, so if I compare these frequencies here, this goes over twice the length, while this one here goes over 4 times the length, which means that these frequencies are half the size of the other frequencies, which means by having a closed side with an open side, I can actually have a lower frequency or a lower pitch to create now more of a bass tone as opposed to an alto tone, for example. So I'll give you some examples of that. So let's say in this case, I'll take this guy, I can beat it on the table. Highish frequency. I'm going to put this cap on here, close the side. Now I've cut the frequency by half. So for this guy, pull it off. Higher pitch, again, close the side. Increase the frequency by half. By having a closed side with an open side, you can now do the bass tones as opposed to the soprano or alto tones when you have it in the folder. Also notice that this thing also goes into one of its lengths, which means the shorter the length, the higher the frequency. So now if I compare the two, so by shortening the length, you're also increasing the size of the pitch or increasing the frequency, which allows you to get higher notes, again, in that soprano alto range, as opposed to a bass tone. Which why is, again, if you look at the flute, when it has the different holes that you push into, again, the closer you are to the side or to the middle, that's the higher the pitch that you're going to have because you're making a shorter resonance chamber, as opposed to moving more to the outside, you have a longer resonance chamber, which gives you a much higher, lower frequency. Okay? So these are the standing waves. So again, we have interference. So we can have interference by having, again, path length difference, or we can have interference by, again, superimposing opposites moving waves on top of each other to create a now standing wave. Another type of interference is actually what we call a temporal interference. So this is an interference which occurs over time. So how does this one work? Well, first, let's talk about these guys. So what I have here are 2 tuning forks attached to 2 boxes, where each one of these boxes has a closed side with an open side, which means I'm now creating quarter wavelengths or 3/4 or et cetera inside of here. This thing is now attached to the box, which means when I vibrate the tuning fork, that's then going to vibrate into the box, create then a standing wave inside of the box. Which means that the box inside will be at exactly the same frequency as that of the tuning fork. This one, I have the same thing. This thing has exactly the same tone. Right? It's exactly the same tuning forks. Now, some cool things I can do with this is I can actually cause this one to start vibrating with never actually touching it. So here I can take this. cause this guy to actually vibrate. Nothing. So what's happening here is I'm causing the tuning fork to vibrate, which causes the box to vibrate at exactly the same frequency as the tuning fork, which sets up a standing wave inside of the chamber at exactly the same frequency as the tuning fork. Having this guy across from here, then will send that wave inside of this wave, causing the same frequency to be vibrating inside of the chamber of the box, which then causes the tuning fork to start to vibrate at exactly the same frequency as this one, when it's like this. However, when I put on the damper here, what I'm doing in this case is I'm adding different mass to it, which changes the frequency of that tuning fork, which means when I do the same thing, I get nothing in this case. Because now the standing wave, which is inside of the box, is different than that of the tuning fork, which means the tuning fork will not actually start to vibrate. This is what we actually call resonance. So what happens is I can force a vibration into something else by matching the natural frequency of that object. This is called resonance. So I'm using this one to create a resonance inside of this one to cause it to actually start to vibrate. Now, this is something that happens in nature all the time, especially on things that we construct. Everything, turns out, has a natural frequency to it. Which means that, for example, if you have an earthquake and you have a building, if the earthquake has a particular vibration that it's vibrating at, that matches the natural frequency of the building that's sitting on top of the earthquake, what's the building going to do? It's going to start to oscillate at exactly the same frequency, which is that resonance frequency. If it starts to oscillate too big, which will happen is you'll actually cause this thing to increase its amplitude, and then the building's going to fall down. This is the bad thing. This will happen on bridges as well. For example, those who are in the military or have been in the military, usually when you are marching and then you get to a bridge, they ask you to do what's called break cadence. What that means is instead of everybody marching in step with each other, now they have them just walk whatever it is that they want to walk, because they're afraid that they're going to match the resonance frequency of that of the bridge, causing the bridge to actually fall down. So, show you some examples of this. So this is the first one. So this is what's known as the Tacoma Bridge. You may know what the Tacoma Bridge is. It's a suspension bridge in California that actually came down. So let's watch it fall down. Just for funsies. Old-timey music.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stored on the bridge and a dog.
Lost the dog, but nobody cares. So, anyway, show you another video of it. This one has an old-timey music. Basically the same thing, just slightly different perspective. I'll start up here. So you can basically see how choppy the water is. So basically what's happening is you have a gale wind, which is then hitting the water. It's then going from the water, reflecting off the top of the water, and then hitting the bottom of the bridge, sending the bridge then into a harmonic oscillation. as the bridge then starts harmonically oscillating, every time it's hit by the wind, it oscillates further and further and further and further, until eventually the harmonic oscillation of the bridge matches the resonance frequency of the bridge itself, which is what causes it to actually come down. So this is what we call resonance. So again, resonance is when you can force an object to oscillate at its own natural frequency to drastically increase the amplitude, which then drastically increases the energy in which this thing actually has. Now, resonance isn't always a bad thing. Here, I talked about buildings coming down and we're showing the Tacoma Bridge falling down. But this is something we use in things like particle physics all the time. So in particle physics, what we do is we take big particle colliders and we smash particles together, watch them break apart, and then see what we actually create. What we're creating then is enough energy to match the resonance energy of a particle, and we're actually creating particles by matching the energy of the particle. So we're basically pulling a particle out of nothing, pulling it basically out of vacuum, causing it to form itself, but then it's unstable and that particle basically decays almost instantly. And then we're seeing resonant spikes of that particle which are actually being created. So there's a whole bunch of different uses for resonances. Some of them are bad, for example, breaking a bridge, pulling down a building, all for matching its resonance frequency. Some of them are good, so again, we can get particles created from them. We can do other cool type things, but total. So this is what we call resonance. So again, resonance is when we can force an object to oscillate at its natural frequency by having something else cause that oscillation. So that's one thing I want to show you here. So what then is the temporal interference that I was talking about? So now we've established that by putting this damper on here, this guy has a different tone or a different pitch or a different frequency than this guy. So now what we want to do is listen while I play these two things simultaneously and see what we hear. So as a reminder, this one sounds like this. This one sounds like this. And that's better. Okay. So I'm going to play these two simultaneously and then try to hear something. Yeah. So what do you hear? Can you hear a wobbling underneath the ball? Type sound. That is what's called a temporal interference. Basically what's happening is you get what's called a beat. So what a beat is if I play two sources, each with a frequency that's slightly different than the other one, at any point in space, what happens then is that I get a modulation of the two different frequencies, which basically means that since they're close to each other but not exactly the same, I start to hear that kind of wobbling type sound. That wobbling sound is what we call a beat. So let me show you what the beat actually looks like. Grab open the part over there. So this is what we call a beat. So basically what's happening here is I'm having two frequencies slightly different from each other, which means the black one here is one of the two frequencies. The kind of bluish, greenish color one here is a different frequency. So notice what's happening is since the frequencies are slightly different, that means the two aren't oscillating exactly in phase with each other. But sometimes I'm going to have fully constructive interference like here, and then sometimes I'm going to have fully destructive interference such as here. So basically what happens then is as time progresses, I go from having zero amplitude when they're completely out of phase with each other to then maximum amplitude when they're fully in phase with each other, back to zero, back to maximum, back to zero, back to maximum. What that does is it creates this type of wave packets. This type of wave packet is what we call the beat frequency. So that wobbling sound that you're hearing is the difference between the two frequencies, which manifests itself as this beat. So basically what happens here is you get two kind of differences. So in here, what happens then is that this frequency is not this frequency or this frequency, it's actually the average of the two frequencies. So you get the average of the frequencies here, but the beat itself turns out then to be the difference of the two frequencies then divided by 2. So this is the portion which is known as the beat, which is causing that wobbling type sound. The other one is the overall tone at which it is that you're actually hearing. So why do I care about beats? Well, beats allow us to do a lot of different things. So for example, in music, I'm gonna go back to Derek because he's the only one that said he plays guitar. If you have a tuner, for example, in music, what it's actually measuring is the beats. So what happens is the tuner plays a tone, your guitar string plays a tone, and then what it does is it measures the beat frequency between the two, and then tells you how you should change the tension in the string to tune the guitar so that you get rid of this beat frequency. This allows you to actually be able to do that. Other portions of using this is used in sonar all the time. So if you were in a submarine and you're trying to figure out if something is coming towards you or away from you, or etc., you're actually using beat frequencies to see what's the change in the frequency to find out how fast the object is moving or how fast you are moving towards that object, which then tells you if you should turn or not. This is also used in things like ultrasound. So for example, if you want to know, and you want to measure the heart rate of a fetus, for example, you send in ultrasounds. Those ultrasounds then hit the heart, bounces off the heart, and when it bounces off the heart, you also get a beat frequency because it changes the frequency at which the wave is coming back to the ultrasound machine there, or the monitor, which then tells them how fast the baby's heartbeat is moving, which then allows you to be able to measure the baby's heartbeat. So beats are used all the time, basically, in any type of science. But again, all the beat is the beat is simply the difference between the two frequencies, which is what we call the beat. The beat, again, is that modulation. So we hear about is this packet here, which is the modulation of the two frequencies. So that's what we call a beat. Now again, this is a temporal effect, unlike all the other interferences we've looked at, which were a spatial effect. So that path length difference and standing waves all had to do with spatial orientation. This one has to do with time instead. So this is called a temporal interference as opposed to a spatial interference. So let's write all that down. So the temporal interference here is what we call the beat. What we care mostly about is the beat frequency. So the beat frequency turns out just to be the difference in the two frequencies, which in this case I'm going to write as the absolute value of the difference between the two frequencies. This is what we call the beat frequency. Again, this thing occurs over time, not over position. So this effect over time, not over position. Which basically means that here the effect, I don't have to move from one location to another location. I sit my butt still in the same location, but I have to hear it over time. Now, it turns out as a person, humans can usually only distinguish a beat frequency of about 15 hertz or less. So for humans, we can hear a beat frequency of about 15 hertz. Anything higher than 15 hertz, we don't hear it. Our brain just doesn't distinguish it. So anything about 15 hertz or less, then you'll actually hear that modulation. So cool. So I'm going to wait to do some examples of this. I'm going to wait until we talk about the last topic, which is what we call the Doppler effect. So let's start talking about the Doppler effect. So what's the Doppler effect? So the Doppler effect is an apparent shift in frequency due to motion. This is what we call the Doppler effect. So this is an apparent shift in frequency, pitch, due to motion. So as my object moves, or my source moves, or my observer moves, I then get an apparent shift in frequency. So this can basically happen one of three ways. So either the source is moving, or the observer is moving, or both are moving. So these are the ways that we can actually create a Doppler shift. So let's show some examples of Doppler shifts. First one is our friend, Sheldon Cooper.
Sheldon, there's something I want to talk to you about before we go to the party. I don't care if anybody gets it. I'm going as the Doppler effect. No, it's not. If I have to, I can demonstrate. Terrific.
Hi.
Hello.
So what are you supposed to be?
Me? I'll give you a hint.
Choo-choo train?
Close.
A brain damaged choo-choo train? I still don't get it.
I'm the Doppler effect.
If you have some sort of learning disability, I think it's very insensitive.
Why don't you just tell people you're a zebra? Why don't you just tell people you're one of the 7 dwarves? Because I'm Frodo. Yes, well, I'm the Doppler effect.
All right, so let's do another one. So this one is basically a guy's going to be playing a horn, and we're going to watch what happens from 2 different perspectives. Right? So basically, he's going to be playing a horn inside of a car, and then we're going to look at what happens from the perspective inside of the car versus the perspective of somebody standing still on the side of the road. So this is what we're going to watch here. Skip forward. So while the car was moving towards, it was at a higher pitch, again, a higher frequency as it was moving towards the observer, in this case the camera. And then as it moved away, you can hear it shift downward. Right? It became at a frequency which was lower than the original frequency at which it came in. So this is, again, the Doppler effect. So again, the Doppler effect is an effect which happens due to motion, primarily relative motion. So there has to be a relative motion between an observer and a source in these cases. Right? Again, this can happen in one of 3 ways. The second one only shows a moving source, but I can also cause the observer to move to get a Doppler effect as well. So again, these are my 3 different ways I can get it. I can have that it's either the source is moving, or the observer is moving, or again, both of them can be moving simultaneously. So what's physically happening? So this is a good demonstration of what's actually physically happening. Show this one here. Oh, you can't see anything. Fair enough. So here's my source. My source is moving then towards the front observer and moving away from a back observer. So basically what's happening is the source is creating sound waves which move away, which move at the speed of sound. So basically as these guys are moving away, they're moving at the speed of sound. He's giving it off at a particular time because it's given off at a particular frequency. which means that each one of these are given off at exactly the same period away from each other. So this is just showing the wavefronts. Now, let's look at the perspective of the front observer. For the front observer, as the source is moving towards the front observer, what happens then is what? When he gives off a pulse, by the time he gives off a second pulse, the first pulse has moved a certain distance, but the car is also moved, or whatever the source is, has also moved a certain distance, which means that the wavelength, or the difference between the consecutive pulses, is shorter than the actual wavelength which should be given off. So if the source was stationary, what you see in that case then is what? They wouldn't be as squished up on this side, they would be equidistances at all times. Okay? But as it's moving, the sound is moving in this direction, but the source is also moving in this direction, which means that the distance between consecutive pulses has shortened due to the motion of the car, or whatever the source happens to be in this case. Now for the back observer, the opposite is true. So by the time it gives off consecutive pulses, the car has moved away, which means the distance between the consecutive pulses has been elongated relative to the actual wavelength of the pulses that it should actually be. Which means that what causes the shift here for the moving source is that you get an apparent wavelength which is shorter than the actual wavelength that the wave is actually giving off. On the backside, what happens then is that the wavelength actually becomes larger, which means that the apparent wavelength that you're measuring in this case is then larger than the actual wavelength of the wave itself. Okay with this? So that apparent wavelength then in our brain corresponds then to an apparent frequency. So as you shorten the wavelength, you then increase the size of the frequency, because remember the velocity is equal to the wavelength times the frequency. So since the speed of the wave is fixed, if I decrease the wavelength, I have to increase the frequency. On the backside, since I'm increasing the wavelength, I have to decrease the frequency, which then causes that shift in frequency. Now, if this one unfortunately doesn't show that, talk about these other ones here in a little bit. If I was looking at the moving observer, what happens in this case then is he sees it at a different velocity. We'll get there in just a second. So basically, let's start kind of analyzing these. We could probably do the first one. So let's first look at a moving source. So let's look at the moving source. So let's say initially my car, for example, is here. Let's say it's moving in this direction with Vs, which is the speed of the source. And let's say at this time, let's call this T0. This gives off a wave pulse. That wave pulse now is here. Okay, so this thing has moved out, and this is going to be equal to our wavelength. At some later time, let's call this later time of T1, my car is now here, still moving to the right with the velocity of the V source, but it has moved a distance here. Right? So this thing has moved this distance in this direction. Now this wave pulse, which was given off initially, has now moved and is getting bigger in size. So this thing is here, which means the wave itself has also moved from this location here down to this location here. So it has moved this distance. But at the same time, this one then is going to give off a secondary pulse, where that secondary pulse is now going to be sitting here. Which means that this distance here, we draw that in gray, is going to be what we call the apparent frequency, and we call that the prime, or an observer on the front side. For an observer on the back side, he's going to be looking at color I haven't used yet. No. So I'll use this one. So he's going to be looking at a longer wavelength, which I'm going to call lambda then double prime. Cool. Now, what happens then is that the time it took for this one to go from here to here, and the time it took for this one to go from here to here, all happened in that same amount of time, which is simply equal to the period. So that means T1 here is actually equal to the period. So this is the amount of time it has gone. So it's gone from the initial time up to time 1, where time 1 then is equal to simply the period. So let's look at lambda prime. So lambda prime then, which is then the apparent frequency, is then going to be equal to what? Well, it's going to be equal then to the distance between the distance at which the wave itself has traveled, this distance here, versus the distance at which the car has traveled, which is now this distance here. So this is going to be my apparent wavelength. So let's call this, I don't know, let's call this X wave, and let's call this one X car. So my apparent wavelength in this case then is going to be what? X wave minus then X car. Now, since the wave is moving at a constant speed, our second kinematic equation says we can ignore the acceleration term, which means I can rewrite this one as simply the velocity at which the wave is moving. So I'm going to call this the speed of sound times the time, which is the period, minus then the speed at which the car is moving, which I'm calling the speed of the source, all then times the amount of time it has moved, which is also equal to the period. So then this is then equal to what, the speed of sound minus the speed of the source, all times the period. But since the period is inversely related to the frequency, this is now going to be the speed of sound minus the speed of the source, all divided by the frequency. So this is what we're going to call the apparent frequency. So this is the apparent frequency at which it is that I'm sending out. Actually, no, not the apparent frequency, the actual frequency. Now, on the left-hand side, though, we also know that speed is equal to the wavelength times the frequency, which means we can rewrite the left-hand side as being the speed of sound, because that's how fast it's moving, divided now by the apparent frequency. So this is the frequency at which it is that we think we hear the sound at. Now, let me cross multiply. So I'm going to bring this term over here, divide this guy over here, bring that term to the other side. So what I finally get then is, by this logic, the apparent frequency then is actually equal to the frequency times the speed of sound divided by the speed of sound minus the speed of the source. So this is when the source is moving toward the observer. So this is my apparent frequency at which I hear when my source is moving toward my observer. What about on the other side? On the other side, the only thing that's going to be different now is instead of having a minus sign here, I'm going to have a plus sign because the size of the apparent wavelength has now increased by the sum of the two distances. Right? So again, this one has moved this distance, this one has moved this distance, which means that this total length here is going to be the sum of those two distances. So basically what happens then is if I follow the same line of logic, I get then that the apparent frequency then is equal to the actual frequency times the speed of sound divided by the speed of sound plus the speed of the source. So this is what happens when my source is moving away from the observer. Here I get an upshift in frequency because now when I have the negative sign, I'm taking the difference, which means I have a smaller velocity here on the bottom, which causes the frequency to go up. When it's moving away, the positive sign makes the denominator bigger, which causes the frequency to go down. Okay? Sure. Okay? So again, what's happening here physically is as the car is moving, the distance you perceive between wave crests is now smaller because the object itself is also moving, which means that you hear or at least you preserve a different wavelength than what it actually should be, which then manifests itself then as a different frequency as it's moving towards it. Same thing as it's moving away. Here I have a different wavelength. The wavelength is actually bigger, which then corresponds to a lower type of frequency. So I only got like a minute, so I'm not going to bother writing the other one down. We'll do that tomorrow. We'll look at what happens when the observer is moving as opposed to what happens with the source is moving. And then we'll put those two things together, and that's what we call the Doppler effect. So the Doppler effect actually has both scenarios automatically. Right? What's up?
Do we have a class on Friday?
Do we have what?
Do we have a class on Friday?
We'll find out tomorrow. So the answer that is probably not going to happen. We'll probably take right out, but we'll see.
Why wouldn't we?
Because we'll be done with all the stuff tomorrow.
And for the cheat sheet, we'll have
Yeah, we'll talk more about that tomorrow. So tomorrow we need to finish this up, do some examples, do a review, and then give you group assignments. So if we get through all that, then we'll have Friday off, unless you want to start the next year. Which I'm assuming you do. Okay. What's it? Today I've observed from 1 to 2. I'm in today.
I didn't know where it was.
Tomorrow.
I was like,
Alright, see you guys.
Weekend, I can bring my stuff home. And then we can always meet on Zoom. Otherwise, in person and full, I have tomorrow. Oh yeah, I can bring home my weight column and then we can just meet on Zoom. What's up?
Can we meet with you for office hours today?
You sure can. Want to do the same thing as